This lesson deals with supplemental problem 2.14. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems on page 28. This supplemental problem is based on an article in what's called Poptronics. This is a renaming of popular electronics in the first volume, number 6. In linear circuits like 201 and 202, we solve for transfer functions, where we solve for an output over an input, and that would have some expression or some equation like minus R2 over R1. And then knowing that relationship, you could predict any other output by simply multiplying the input by that transfer function. For nonlinear circuits, this isn't possible because we don't have a closed form solution. The closest idea to this is plotting V out versus V sub s, then using that to project values of V out given V sub s versus time. Take something that we know. Let's take the bridge rectifier and let's plot V out versus Vs, assuming that the diode's turn-on voltage is around 0.7. Let's use that then to predict what V out would be if the input was a 2.5 volt peak triangle wave. On page 43 of the Chapter 2 lecture notes, we had an expression for the output voltage of a bridge rectifier. When the input was between two diode drops, the output was equal to 0. Well, we could sketch that if we plotted V out versus V sub s. We'd have 0 volts between plus and minus 1.4 volts, in other words 2 times 0.7. When the input was greater than 2 diode drops, in this case 1.4, the output was equal to the input minus 2 diode drops. The slope here is 1, so any change in V sub s will be the change in V out. Likewise over here, when the input is negative enough, say 1.4 volts or more negative, the output is the negative of the input minus 2 diode drops. In other words, a change over here would produce a change in the output, but there's a sign change. We're going to have a negative slope here. Let's use this to plot the output voltage if the input voltage was a 2.5 volt triangle wave. Here's our V sub s. We don't have time. Let's put time this way. I'm going to draw a 2.5 volt triangle wave. I'm going to go from 0 to 2.5 volts, back to minus 2.5, back to 0. This peak, I'll say, will be at T1, crossing 0 at T2, negative peak at T3, and back to 0 at T4. We start out at 0, and we eventually get to 1.4 volts, a little bit less than time T1. The output voltage is 0, and then an increase in voltage of 1.1 volts results in an output increase of 1.1 volts from this time to the time T1. And we come back down, the same thing happens, but we're going in the opposite direction. We're decreasing. And then from here back to here, we're going to get 0 volts out. Then we're going to decrease by 1.1 volts, but we're going to have a slope change of minus 1, so it'll be plus. We'll come back down again, which is this part here, and then we'll have 0 volts back out again. Knowing the transfer curve, we can predict output voltages versus time if we project the input versus time as a separate axis and likewise time this way. And this is supplemental problem 2.14.